Right, so, hello everyone.
Hey, Tim.
So, firstly, a little bit about who I am. I'm the CTO at Paramus. You may remember me from other talks such as the keynote about an hour ago. I've been working with OSGi for quite a long time, and I'm co-chair of the IoT expert group. So I do a lot of stuff with IoT standards as well as other things, so asynchronous distributed systems. And what I'm going to be talking to you about today is more of the asynchronous stuff and a bit less of the IoT stuff. But it's interesting how they still have an impact on one another. So, a quick introduction to reactive programming. Firstly, what is it? Well, it's basically just a set of principles. You've got large volumes of live data, where live means it's happening now or very recently. And it might be historic, but the whole point is you're not storing this and batch processing it later. You're trying to do something as a result of stuff that is really happening or happened at a historic point of time, but you're replaying it as if it's live. And the changes should be reactive, meaning that they are reflected immediately. So when something happens that is a trigger, you then react to it. That's where reactive comes from. All your operations, therefore, must be stream-centric. Because if you're having to deal with the whole stream before you can come up with some kind of result, you are no longer reactive. You are not reacting to data as it arrives. You're doing batch processing again. Now, as part of this, you need to control the way that you use your resources. And they do this using asynchronous exchanges of data. So you can actually decouple processing from the production of the data events. And this may be asynchronous within the same process, or it may be cross-process. And because it's asynchronous, you need back pressure, which is also non-blocking. You can't just block the thread and say, I am going to prevent you from sending me more data by stealing your thread. That's not allowed. That's not reactive. Reactive is about saying to them to slow down, but being prepared to cope with the fact that they might not. And the Reactive Manifesto has lots of stuff about this, as does the standardization effort, which is at Reactive Streams. These are places you can go to look up more about reactive programming in general, if that's your interest. Now, Reactive Java does exist as specification. So the Reactive Streams initiative that I talked about, there is a spec there. And that's where org Reactive Streams exists. There's a specification, there's a TCK. You can check that what you've done meets the requirements of those interfaces. But it doesn't define an implementation. There is no implementation there. It's just the API, the spec, and a TCK. You have OSGi Push Streams. These are something that is a bit different. There is the org OSGi util Push Stream API, which is defined. And it's a self-implementing API, meaning that if you get a copy of it, you have an implementation to use right there. We also have the Flow API in Java 9. And this is basically just a rename spacing of the Reactive Streams API. People think it might be something different. It's not. It's the same thing in a different namespace. So the primitives are therefore the same for Reactive Streams and Java 9. Because it is just the same thing with a slightly different name. You have a publisher, which is the thing that is going to give you data. You have a subscriber, who is the person who is consuming the data. The subscription represents the connection between those two things. And you have a processor, which is something that is both a subscriber and a publisher. It's going to consume some data and then send on some data as a result. In Push Streams, we have a very similar set of primitives. We have a source of data called a push event source. You have a consumer of data called a push event consumer. The connection is the fact that in this case you get a closable out of the thing, so you can close the connection. And you also have a push stream, which is effectively the pipeline that you're using to build between these two things. So very similar primitives with different names and some slightly different semantics. So now we're going to talk about actually being reactive. We've seen what the Reactive Manifesto is talking about, what we're trying to do. So in the following examples, we're going to have a monotonic infinite sequence starting at 0, publishing every 50 milliseconds, and we want to consume the first n events from this sequence, and print out when you're finished consuming these events. And this is simple, obviously. It's practical, though. This is something that you genuinely want to do, some kind of consuming of data events and doing something as they arrive. And the sequence is infinite, but you need the thing to terminate, right? And this is why short-circuiting is necessary. It's frequent that you'll be dealing with a stream of data that doesn't have a natural end. You know, there is no natural end to number of clicks coming in on your website. There's no natural end to temperature readings from a sensor. You just have to read until you're done, and then you stop, and the data still exists, you're just not interested in it anymore. And we're going to compare push streams and reactive streams. So, this is going to be a slightly more code-heavy presentation than some of the ones you'll have seen from me in the past, so hopefully that will be to people's tastes. Right, so what we have here is the first example code. So there's a bit of setup boilerplate you can see here with the start and stop, but the main body of this thing is in this test method. So you can see I'm going to be able to call up to a certain number of times. I have this thing which is a simple push event source, so this is going to be the source of my events. And when something connects, I'm going to start delivering. Delivering is pretty easy. I basically just go publish an integer every 50 milliseconds and just keep going. And then on the consuming side, I'm creating a stream from this source. I've got my limit, so this is the thing that says only give me the first n things. And then for each of them, I am going to print them out. And then when I finish, I'm going to say finished, or if I break, I'm going to say that I encountered a problem. And then the get value is effectively a way I make this blocking. So this is naturally a non-blocking API, but I don't want my program to terminate before I'm done. So I get the value, which causes me to wait until I've finished processing the stream. So you wouldn't normally do that in an infinite scenario. You'd go off and do something else. But this is a simple play thing, right? So what I now want to do is to go and run this. So you can see here I've got go, and I can do test 20, and you can see it prints out 20 things. And would you believe the delay between each of those items was about 50 milliseconds. So this was a pretty simple way of doing that kind of processing, right? We had nice native features for doing things like limiting the length of the stream and processing it. So far, so good, right? We had this thing called the simple push event source. It's actually very powerful. I didn't show all of its features because we don't have time to go into really deep detail on all of these things. I need to give you a broad overview. But it is a powerful thing that can multiplex lots of consumers from a single stream. We just had a single consumer, so we're not really using it to its full capability, but it can do that too. It's buffered, so it means that even though in this case my consumer was fast, if my consumer was slow, that would be okay. It wouldn't block that producing thread. And you've got callbacks, which mean that you can do lazy event generation. You saw that I triggered my my sending of the events using a connect promise. That meant that it was only once someone actually connected to my simple push event source that I started generating data. And then when they finish, I can detect that too, and I can stop generating data. So this is really cool. The push stream had quite a familiar model for those of you who've seen it before. That looks like Java 8 streams, right? And there's a reason for that, because it's really heavily influenced by Java 8 streams. So all of the Java 8 streams operations you know and love, you have on the push stream. And there was no dependency on the rest of the OSGi API. I know I'm running that in OSGi to get Go shell, but that's the only reason I'm running it in OSGi. The rest of the code had no OSGi dependencies at all. So you can do this in standard Java. Now the reason I didn't stand up is because I know the next thing that's coming is I need to show you how this looks if you use reactive streams. So Reactive Streams, you'll see we've got some very similar boilerplate for setting up. And then actually in this test, you see it's pretty short. I create myself a new subscriber, which is interested in up to some number of things. I have my publisher, which on subscribe creates this subscription and passes it in, and then publishes it. So this looks really simple, right? Well, it sort of does, except I've actually got to have that subscriber. So my subscriber implements the subscriber interface, and I've got this latch which I have to be able to work out when it's done. And I've got to implement the onComplete, the onError, and the onNext. So rather than having lambdas, I've got to implement this interface because it's got multiple methods on it. And then onNext, I have to work out whether I'm going to either cancel my subscription or request more data. So a little bit more complicated, right? There's more. It turns out we also need to implement the subscription. And the subscription, this is the thing that's going to handle the processing of data that's coming through. And you can see I've got some synchronization in here, and I've got the wonderful handling the request when they've asked for more data and processing all of this. And I have to deal with closing. And actually, rather than being the kind of 60 lines that we were before, I'm 170 for this really simple example.
Is that really the optimum thing to implement that?
So don't worry, we'll get there. But just to prove, you know, this thing that's been implemented, I can run it up again and I can get it to print 20 things, and it prints 20 things. Now, that looked really horrible, and it wasn't fair. As Christian said, this isn't what you should be doing, right? Don't do this. Reactive Streams is a pure API. I said this before. It's not self-implementing. Any non-trivial application isn't using an API. It's using an actual implementation of the Reactive Streams stuff. And this is true of Java 9's Flow API as well, right? There isn't stuff in the VM that you can use. You have to get a library. So if we were being fair, we wouldn't use the Reactive Streams API. We would use a library to compare against Push Streams, because that's apples and apples. What we had was showing how you do the beginnings of a basic library implementation for Reactive Streams. So RxJava, one that people have heard of, it's originally from Netflix. It's used all over the place, and that's something we'll be using. Also, you may have noticed that where previously we had a 50 millisecond wait, this one didn't. We'll come on to why that is later. Oh, and, you know, just to say what we're doing now, we're going to look at RxJava. So this is a slightly fairer comparison. Nothing makes you appreciate screen real estate like projecting while you're dealing with it. So here we go. We have, in this case, an observable. So the observable is like the base type in RxJava. This is the thing that is going to provide you as a source of events. In this case, we're saying it's a range. We can't say infinite, but 0 to max int is a pretty long stream. And in this case, we've got take, which is roughly equivalent to the limit we had before. So we're going to take a certain number of things. And then on next, we're going to print out the data. On completion, we're going to print out finished. And finally, we're going to say if there was a problem, we encountered a problem. And then we subscribe to this thing. So that's the thing that's going to say, OK, start processing. And as you can see, this is nice. This is really short. So let's go, run it. And you'll see, again, it does exactly the same thing. But it still ran quickly, right? So the example was really short. That is the shortest of the examples, definitely. but it still wasn't actually a fair comparison. And this is for a much more subtle reason. The other examples were doing an async push. There was a thread that was pushing data in. In this case, you may have noticed part of the reason it's shorter is there's no setup to produce an executor. There is no other thread going on here. And that's because most of the Rx Java stuff is actually making data on demand. It's not consuming data that's been pushed in. It's saying, I'm ready for the next thing now, and the next thing is produced as a result. It's still asynchronous, but it's not asynchronous push. And this is why both the raw API version and this are running faster, because there is no 50 millisecond delay. There is no, this is the rate at which events are coming. It's just, give me the next event, give me the next event, give me the next event. So we actually do need to put publication on a different thread. If we're going to be properly comparing things that are doing the same work, and we remember our original statement was these are events that are happening every 50 milliseconds, then the example we had is insufficient. So, one more time. So here, you'll note something rather more similar to what we had before. You have some thread pools here which we need to maintain in startup and shutdown. And we've got this suddenly slightly different behavior, which is that we're creating our observable rather than using a range. And we have a deliver method. And we've still got the take, but we have this observe on. And this observe on is the thing that's actually forcing it to do a thread handoff. But we have to make it do that. It won't do it implicitly. And the rest of it's still the same. Now the deliver, you'll see, is very similar to the thing we had before. This is saying that when someone makes a connection, we're going to, on a different thread, start pushing stuff in every 50 milliseconds. Oh, still running, so I can bring this guy back up, and in this case it's called test2, and run it 20 times. And what do you know? We are finally at the stage where we have two things that actually do the same thing. So it turns out that when you get it to the point that you're doing the same thing, the code is really similar. I mean, you've got some different type names in there, but you could easily recognize what it's doing, and they look almost exactly the same. They're the same length to within like 1 or 2 lines. It's really, really similar. And it's actually not that unsurprising, because right at the start I showed you a table, and there are primitives doing more or less identical jobs. So this is not a surprise that you end up, if you want to do the same reactive kind of programming, you get the same answer in terms of the code. It's being dictated by the abstraction that you've chosen. So what is the difference? If I'm saying these two things are basically the same, why are there two different things? What is the difference between them? So the first difference is actually right at the start. It's how we create the connection between these two things. And it's the way we connect the source and the consumer is different. So with the push stream, I told you there's this closable, which is returned by the method that connects the source to the consumer. Whereas in reactive streams, the publisher is connected to the subscriber with a method that's void. So that means that the person who connects these two things in reactive streams cannot close the stream. Once they've made the connection, their work here is done and they can't close it. The way that you would have to close it is to get hold of the subscription, which is purposefully hidden from you. So this is an important difference. The person who is outside making the connection loses responsibility with a reactive stream. And whilst there is a disposable in Rx Java, it's not actually doing the same thing. A disposable is saying that from the end of the stream, I'm done, rather than saying in the point at the stream where I've created it, okay, close from here down, finish the buffers. Also, as you saw, in general, a reactive stream is not Lambda friendly. The subscriber has 4 methods and it actually has to have state because it stores its subscription, which is injected into it after it's been created. Now, it doesn't change, but it is something that can't be final because it's not added at construction time. So specific libraries try to work around this. It's why you saw on the observable, you had the ability to register separate lambdas that aren't subscribers. But it means that actually the base API isn't very friendly.
Can pass the lambdas to the subscribe methods?
So you can pass lambdas to the various methods as long as you couple to a particular library implementation. So the observable accepts lambdas, but the publisher does not. So the Reactive Streams API is not lambda friendly. You have to couple to a library. So the next difference is the way in which events are propagated. So a subscriber always makes a request before data can arrive. You saw that in the examples. You actually had make a request for the next data item. When I was using the raw API, I had to initially say, give me something. Which means that, and also the data can't be delivered concurrently. Because of the rules in the Reactive Streams specification, you request something, and then the various methods won't ever be called concurrently. You will receive an on next, and then an on completion. That's the way that it's designed to be called, and it's always a sequential call. It's designed that way to make it easy to be thread safe, because you don't really need to worry about it, because you're never being called concurrently. There's always a memory barrier. It also reduces the possibility of exhausting the CPU, because you're not going to be burning multiple threads as fast as you can. But it's not always the right model. So a push stream is different. A push stream pushes data whenever. Data arrive, push, push, push. Are you ready? I don't care. Push, push.
But isn't it the same in reactive streams? You can also push just?
Nope. In a reactive stream, you can't push data into the subscriber until they have requested it. That would be a violation of the spec. So, in general, event delivery in a push stream is concurrent. You can use sequential to change that, but in general, if multiple threads are publishing in, you will get called on multiple threads. Your pipeline functions should therefore be stateless or thread safe in some way. So that is then your responsibility, which it isn't in reactive streams. Also, back pressure in push streams is best effort rather than strict. And this is the difference. So as I'm saying, when you have a subscription and you say request 1, they can give you one thing immediately, but they can only give you one thing until you make the next request. They cannot give you another item.
They can, maybe not.
No, they can't. That's a violation of the spec. That's no longer a reactive stream. That's something else.
Yeah, maybe. That's true.
In push streams, if you ask for a 10-second delay before the next event, then you could get the next event in 3 milliseconds. And that is allowable. And in most cases, nobody cares. Right? In most cases, there is no visible difference, and the code that you tend to write tends to be, because they're functional in style, tends to be a stateless function that does transformation. So nobody really cares that these things are different, and you end up with examples that look like the ones I showed you, which are effectively identical. The differences come when you start trying to deal with more interesting aspects of the stream. And this is the source of your event having a different characteristic. So a cold source is one that can be restarted from the beginning at a later point in time. So if I have a collection, like a list, I can always go back to the beginning of the list and start replaying the data again. And I can do that over and over and over. A hot source is one that provides data to me, and it's live data, and you can't go back and rewind time. because there's some kind of temporal component to the data was here and now, and you can't go back and say, what was the data back at the start? It's gone. So temperature readings from a sensor, or if you're at the trains demo in the main foyer area, then the location of the train, that is a hot source of data. The historic data just isn't there, and it wouldn't really be that meaningful either. A pull source is one that is on request, so it is possible to be both hot and pull. So if you've got a temperature sensor that gives you a reading when you ask for it, and you say, what's the temperature now? And then again, what's the temperature now? You can't say, what was the temperature 10 minutes ago? It can't tell you that. A push source, on the other hand, is data that's happening as a result of something. So again, the OSGi train is going over a tag, it's reading that RFID tag, and it's sending that data because it's happening as a result of the train moving. That is a push event. You can't say, give me an event now, because there may not be a tag there, it doesn't know. It will just tell you when it encounters a tag. So these are two orthogonal things that are both characteristics of your stream. A cold source is almost always a pull source because it has some historic buffer of stuff, and you say, give me the thing, either the latest thing or a thing from the past. But it doesn't tend to be a push event-driven thing because then you don't usually have a historic set. So reactive streams actually work really well for a pull-based source, as you've seen. You can really simply grab stuff from this range that was generated and just keep grabbing more data and process it. And this is because data is only sent after a request. You have the subscription and you ask for the next number of things, and then it will give you that number of things. And it won't do anything else until you ask for more stuff. A push stream, however, works well, surprisingly, for push type sources because that was what it was designed to handle. And this shows up when we start trying to cope with a slow consumer. So when your event consumer is fast, like it was in my examples, it's really easy to process data because you just process it really, really fast and you never get overwhelmed because you're much faster than the rate of event production. But if your source is faster than your consumer, you have a problem. And this is why you need buffering. A reactive stream must always buffer if you've got a push source, because the whole point of a reactive stream is it can only send you data when you request it, and if the data is arriving from the publisher asynchronously and at some kind of random interval, the data may arrive when you've not requested anything. And unless there's a buffer created, it will fail. A push stream, on the other hand, uses the incoming thread to receive data. The thread that's pushed the data in is the one that propagates through until you reach some kind of thread switch boundary. So if you push on multiple threads, that's implicitly handled in parallel. A long running or blocking operation should therefore use its own thread. You should not steal the incoming thread to do a long running or blocking operation. And therefore you do still have the concept of buffering in a push stream, and it's valuable. And it's valuable because it releases the publisher's thread to go off and do something else. That's not your thread to steal. But this is only part of the solution, right? Having a buffer is a small and significant but small part of fixing this. Because your buffer can't just grow forever, right? You've got an out-of-memory error kind of problem if your buffer just keeps growing and growing. So a buffer is there to solve bursts, but not a long-term speed mismatch. A buffer protects you against, I got 5 events really, really quickly, but on average, my consumer is faster than my producer. It doesn't deal with, my consumer can cope with 10 events a second, and my producer produces 100 events a second. Buffering does not help you. This is where you need some kind of ability to fan out to process that. If you need to process all those events, you have to go in parallel. And you have to go in parallel by fanning out because you've got a strong requirement that you can't concurrently call your consumer. Therefore, you have to spread the processing over multiple reactive streams. This often uses a new process, so this is what akka does. Akka does fan out by spreading work to new processes, spinning up new processes and splitting those things. But a push stream doesn't have to do that, because a push stream can just use more threads because it's allowed to be concurrent. A buffer, therefore, allows you to scale up the number of workers. So if you have a function that is slow because it's doing a significant computation on one CPU core, but you're on an 8-core machine, you can simply increase your throughput by saying, let's use more of the cores by using more threads. Therefore, the buffer in a push stream actually can help you to solve not only the burst problem, but also a long-term mismatch problem. But we can only get so far by doing this, right? We need to use back pressure to slow down our data source. And in this case, I've been saying reactive streams, you use the request to do this. It helps your pull source, because you just don't get more data, but how does it help you with push? How long should we hold this data? How long should we drop data for? Push streams, on the other hand, return this delay, and this is a delay that should be observed before sending the next event. You may choose to drop messages that occur in that delay period. You may choose not to. A periodic producer may be able to say, I'll just slow down the rate at which I'm producing. If you've got a smart temperature sensor and it says, oh dear, the person can't keep up with the rate of temperature events, maybe I just don't send them so often. But if you've got something that has important messages, it's always hard, right? If you can't drop them and you can't slow them down, it's hard. So in the following examples, we've got an infinite sequence from 0 every 50 milliseconds, and we want to print out the first 500 events. In this case, the consumer is going to take 80 milliseconds per event. Note that 80 is bigger than 50. We've got up to n threads that we can process this stream on. So that's not the correct one. Here we are. So you'll see that actually this is quite a similar setup to last time. We have our simple push event source, we have our connect promise, but we're actually building the stream and we're making it parallel. So we're adding a buffer to fan out the number of worker threads we have. And this is the executor we're going to do our work on. And we're limiting it to 500 things, and you can see here it takes 80 milliseconds to do this. Pretty simple, right? So now, if I do this processing on one thread, we'll see it runs happily for a while. And it runs happily for a while because the buffer is treating this as a burst. But over time, we find my queue fills up, and the whole thing explodes because my buffer was unable to process, unable to hold the data that I couldn't process fast enough. On the other hand, if I increase the number of threads I'm using, we'll see that actually, rather than exploding at about 60 data events, we're processing now faster than we were before, and as a result, we don't have this long-term mismatch. So even though events are coming in faster than one guy can process them, the second guy is fine. And we'll, in about half a second, hit 500 and done. So that was the push stream example. And you'll see that other than making this thing take a little bit longer, I basically have 2 lines, which is to configure my buffer. Yes, but that would be more code. Now, the Rx Java example is a little bit different, as I have to firstly become a flowable, because flowable is the type that actually handles buffering in Rx Java, and I tell it that back pressure strategy is to buffer. I've set the buffer to be 32, which is the same as the default size in the push stream. We're taking 500 things on a different thread, but this is where it gets different. And this is because I have to fan out. So in this case, we've got to flat map our flowable across lots of different threads, which are all observing on another worker. And we're printing out, but we've suddenly got this mismatch where I'm responsible for dealing with all of this fanning out and collapsing, when really all I wanted to do was get parallel processing. So actually this thing becomes much more complicated than just trying to deal with call me on 2 threads. But the end result is pretty similar. So if I run this, you'll see on one thread, it will go for approximately the same length of time before exploding. Come on. There we go. And it does exactly the same thing. The buffer fills up. And if I run it on more threads, then it works. So both libraries we've seen are pretty easy to deploy, but the push stream implementation is small. RxJava is not. RxJava is like a lot bigger. And basically the API you should use matches the use case that you've got. So if you've got a hot push data event coming from your IoT sensors, push streams are really good at that. But if what you have is something that you want to rescale your video stream based on how fast the data is being sent to your streaming video client, much like they do at Netflix, RxJava works pretty well. So push streams work well with multiple threads. RxJava works well with effectively pull type data. And the Reactive Streams API on its own is pretty useless. It's only there as an SPI. Now, I'm running over time, I think.
You're over time. You're not
Yeah.
going to wrap it up in like a minute.
So what I will say is that Reactive Streams API is good for something, which is interop. So a standard push stream can be used as a publisher, and a standard publisher can be used as a push event source. Those things are both possible. You can link these streams together. You don't have to say, I am only going to use one type or the other. And I do have a demo of that, but I think I'm probably not going to be allowed to show it. So if you want to come and see it,
no questions either.
if you want to come and see it, then come and talk to me. There are plenty of details about this stuff online, so you can look at the OSGi specs. The R7 draft spec that's been done actually has the push stream data in it. There's stuff about reactive streams. And please evaluate all of the sessions that you see, not just mine.
Thank you, Tim.